Our next speaker is Professor Fujikawa. Fujikawa, please.
This is a symposium on the spontaneous symmetry breaking, in particular in memory of late Professor Robert Brout. But Professor Anglais gave a very beautiful description. So, including the inflation idea, I really impressed. But you together discussed inflation even before it became popular. So I really enjoyed your paper. Yeah. But anyway, this is a spontaneous symmetry breaking, and Nambu is deeply associated with it. Therefore, Ras, organizer, asked me to talk something about the Nambu from the point of view Japanese, because he said I'm a Japanese delegate. So, so I'm going to explain some, I think, rather private things about Nambu first. So this is a subject, Yoichiro Nambu and the Japanese particle physicists. And when you talk about particle physics in Japan, we start always with those three figures, namely Yukawa, Tomonaga, and Sakata. Yukawa is, of course, well known for the meson theory, Tomonaga for the renormalization theory, Sakata for the Sakata model, and more recently, Maki Nakangawa Sakata mixing of neutrinos. So those three people, all of them are from Kyoto University, but Yukawa stayed at Kyoto, Tomonaga moved to Tokyo, and Sakata moved to Nagoya, and they somehow established the particle physics in Japan. And Nambu started in Tokyo, attending seminars of Tomonaga, and very much influenced by Koba. Koba was the most senior collaborator of Tomonaga when he analyzed, discussed the renormalization idea. And Koba later moved to Copenhagen and educated famous people like Holger Nielsen and Paul Olesen and so on. But anyway, Nambu respected Koba for all his lifetime. And Nambu literally lived at University of Tokyo because he had no other place to live. So he had blankets at his office, and so he slept there. But they shared office. Therefore, before Koba comes early in the morning, Nambu had to get up. That's what Nambu told me before. It's okay. But in Tokyo, you see, there's no job for young people. So young people moved to Osaka City University. They established a new physics department. And those young people get together there around the age of 30s. But although they started the physics department, but no students there. Therefore, they had no teaching duty, so just physics, I guess. Although Professor Nishijima used to say that he went to movie theater in downtown Osaka every day. But anyway, they worked together. And in this period, they generated very impressive work, namely Gelman Nakano Nishijima rule, which Gelman called strangeness. So this was a very good, impressive idea of the let me see, very impressive achievement. And then Nambu left Japan to Princeton. And Nambu told me that Nambu together with Toichiro Kinoshita, and Kinoshita became the real expert on QED later, and together. But of course, not easy to go to the place like Princeton. Therefore, Nambu told me that he asked Tomonaga to write letters. And Tomonaga had many friends there. Therefore, they successfully managed to go to Princeton. And at Princeton, Nambu and Kinoshita together wrote papers on plasma physics. And I guess that might have helped his later research. But anyway, that's the case. And at that time, there are no airplanes, so they went there together using a ship, spending more than 2 weeks on the Pacific. And this is a picture of Nambu at Osaka City University, and many years later, he came back there and to give a lecture there. And this picture was given by Itoyama. And then after Princeton, Nambu moved to Chicago. And at that time, many visitors, short period or long period from Japan. Long means postdoc like 1 year or 2 years. This may be just 1 month or so. By the way, in Japan, we used to have 2 major schools in particular physics. One is the Kyoto Nagoya group. This spiritual leader is Sakata. And Tokyo group. They had no big leader, but many young students. And they were always competing. And my impression that this was very good tradition, but when the internet became popular, then we have no more this kind of groups. So everybody is influenced by outside fashion, you see, in the United States or in Europe. So in a sense, Japanese physics lost its characteristics. And that's a pity for me. But anyway, and while the Nambu, Chicago, many visitors from Japan, as I said, and mostly from Tokyo group. And therefore, they had a good chance to look at the United States, because at that time, to visit the United States was very expensive, because salary-wise, ratio is about 1 to 10 or so. So Japan is very poor at that time. But many people there. But when it comes to the idea of spontaneous symmetry breaking, my impression is that the most ardent followers of Nambu are from Kyoto Nagoya group, and notably Maki and Masukawa. Maki was senior to Masukawa, and Maki was a really nice physicist, and he's well known for the Maki Nakagawa Sakata mixing angle nowadays. And Masukawa, of course, wrote a paper on CP violation. And Masukawa never went outside. And in fact, his first trip outside of Japan was his trip to Stockholm. So that's another thing. Anyway, these are the papers Masukawa wrote together with Nakajima. And you can say spontaneous symmetry breaking. And Masukawa was very much interested in whether coupling constant should be strong or weak or so on, that kind of very detailed. And he spent really years on Nambu Jonara senior paper. So he often used to say that he read all the details of Nambu Jonara senior many, many times. And so he spent years. So he wrote a paper on CP violation in 1972, but that's only his paper on CP. So before that paper or after that paper, Masukawa mostly spent his time on the spontaneous symmetry breaking. So in this sense, Nambu's strongest influence on Japanese physics may be on Masukawa, and Masukawa achieved his own achievement. But one thing I should mention is that no nice idea like angular Brout and Higgs came out from Japan, despite we had Uchiyama and Nambu. And partly because my impression that Uchiyama was somewhat isolated. He was in Osaka, but outside Kyoto Nagoya group, also outside Tokyo group. But anyway, this is a fact. And then that's a personal thing. Okay, if I finally commented on personality of Nambu. And Nambu was, of course, confident himself. But when he once quoted the following short poem in his essays about his young days in Princeton, which was published in Bulletin of Physical Society Japan. And this episode is very well known. But anyway, this is a very poor translation of a poem of the famous Japanese poet called Takuboku. He was a genius, but not appreciated when he was alive, and he died around the age of 26 or like that. But anyway, his poem says something like this: all of my friends looked greater than me today. So on my way back, bought flowers and prayed them at home with wife to ease an uneasy feeling like that. But anyway, this is a very poor translation, but meaning is something like this. And this poem is very well known in Japan. And I like this poem, but I was rather surprised that Nambu quoted this poem. Also, one of the columnists of the biggest Japanese newspaper also talked about this episode. And this episode, in some sense, encouraged the Japanese people, young people in particular, because Nambu also had this kind of hard days when he was young. By the way, Nambu memorized many classical Japanese poems, even at his old age. I recognize this when we had a workshop in Nara. Nara is a capital older than Kyoto, so about 13 or 1400 years ago, capital. And so naturally, therefore, there are many well-known, famous short poems. Short poems are Japanese tradition. And but Nambu memorized many of them. So I was really surprised that even he left. Thank you very much. He left Japan as even after 40 years, he left Japan. But so that is the main part of my personal thing. So I now come to the physics, but still related to the memory of Nambu. And the first subject is spontaneous symmetry breaking in nuclear physics. Nobody else is going to talk about this aspect, so I'm going to briefly mention it. And the major figure in this is Bohr and Bohr Mottelson. This is very important because they received the Nobel Prize for this paper. And this is the theory of nuclear deformation. So idea is something like this, very briefly. Start with a spherical nucleus. Therefore, only vibrational harmonic motion, but no rotational motion. Because quantum mechanically, spherical means really spherical. So no moment of inertia, so no rotational motion. Then due to some internal dynamics, lowest vibrational mode becomes lower and lower and touches the ground state. At that time, dynamic instability induced by zero mode. And then nucleus is deformed with non-zero moment of inertia. And therefore, nuclear rotational motion starts. And so this is just a brief description. And in this analysis, of course, the idea of BCS and Nambu-Jonara-Shinio type of thing, like pairing and condensation, played a major role. But this is the old famous paper. But what I want to mention is not a well-known paper of mine, but this is I have a very good memory of Nambu about this, so I'm just briefly mention it. And I wrote together with Professor Ui. He was an expert on nuclear physics, and he passed away some time ago. And I titled that nuclear rotation, Nambu Goldstone model, and Higgs mechanism, but nowadays maybe we should call VEH mechanism. And the idea is that the nuclear motion is most important mode is the quadrupole vibration, because dipole means center of gravity moves, and monopole is incompressible liquid. Therefore, this is the most important mode. Then you write the rotational invariant Lagrangian, very much like the particle physics. And this is a third Casimir in this specific case. Therefore, this rotational invariant. And we make this local rotation invariant, following the idea of Jan Mills and Uchiyama. So we introduce the analog of the gauge field. but this actually is the angular velocity in this case. But we told this as a background gauge field. And then after the spontaneous symmetry breakdown, potential becomes something like this. And the V, the stationary point means this is derivative is 0. Let me see, this is not true. This is 0. Therefore, linear term must go away. But when this go away, simultaneously, this is the phi 1 mode, phi plus minus 1. This also becomes massless. Therefore, we have the massless Nambu-Goldstone mode appears. And after this spontaneous breakdown, you recognize that inside the Lagrangian, you have this kind of coupling term. This is very much like the gauge field and Nambu-Goldstone mode coupling in the VH type of formalism. Therefore, the zero energy mode can make transition to the background gauge field. That means the Nambu-Goldstone mode are transmuted into the corrective rotational mode if one chooses a suitable gauge, means suitable choice of variable. And this is the analog of the VH mechanism. And the reason I mentioned this is that when I wrote this paper, when we wrote this paper, we sent a preprint to Nambu. And then after 1 year or so, when Nambu came to Japan, he asked me, what happened with this paper? How this paper was accepted by the other people. And this was a very rare occasion because Nambu rarely showed interest in, for example, when I explained him some idea, but he does not say good or bad. And just smile. That means he finds it not so interesting. But anyway, in this case, he rarely, he made a rare favorable comment. So although this is not quoted much, but I still like this paper because of Nambu. So this is so far the rather old stories by Nambu. And then I want to talk about some topics I am now recently working. And that is an idea, something Majorana neutrino as Bogoliubov quasi-particle. And this is also closely related to Nambu because of Bogoliubov quasi-particle. And essential model is the seesaw mechanism. Seesaw means you have the standard model massless left-hand neutrino. You add the right-handed component. Therefore, you can have the Dirac mass. And then you have the very heavy right-handed mass. And the ML is you can usually you set this 0. Okay. But anyway, important point is this one violates parity because right hand is very heavy, but no, you can set this 0, means no heavy left-handed mass. Therefore, if we assume Cp, then C is also violated. If you define new variable like this, Dirac type variable, then that seesaw Lagrangian looks like this. And this is, and epsilon 5 is just a left-right symmetric part. This is a left-right symmetric, this is asymmetric one. So this part breaks C and P. But this looks very much the BCS Lagrangian because these two terms break the lepton numbers by plus minus 2 units. And C and P are deformed this way. So above Lagrangian is a Cp conserving, but C and P are separately broken by this. Then interesting question is this. If C and P are broken in the seesaw Lagrangian, but when you rewrite it but in terms of Majorana, then somehow manifestly C invariant because Majorana is a C eigenstate. So question is what is the basic mechanism? And the conventional seesaw, say, all the textbooks, as far as I know, uses a rather ill-defined C operation. I'm going to explain what I mean by ill-defined. And our proposal is that we use a relativistic analog of Bogoliubov transformation to understand this issue. So I come to the conventional seesaw idea. In the seesaw scheme, people usually define the charge conjugation of left-handed neutrino with this, namely charge conjugation matrix times this object bar and transpose, and the right hand same thing. And the peculiar aspect of this is that this is left-handed, this is right-handed, this is right-handed, this is left-handed. Therefore, if you assume the unitary charge conjugation operator, for example, and remembering this is identical this one, start with this one, unitary operation, using this, you have this. But if you assume this, you get this. But this is 0 because this is a left-handed projection, this is right-handed. So this is 0, and similarly for NR. And this issue is very strange, but this has closely related to the interesting issue of the Majorana, Fermi, and Weil. People often say that when massless, Majorana and Weil are the equivalent because if you use a two-component notation, both are more or less same. But quantum mechanically, not so simple. That's what we recognize. And also, I've explained further. Okay. Therefore, when you define Majorana as a left-handed one and left-handed charge conjugation, and if you do this way, then this looks nice because this is left-handed, this is right-handed. Majorana is a more or less vector-like. But if you write down the Lagrangian for this, Majorana, then using this, you can relate to this. So it looks like to be equivalent. But because this is left-handed, you can write this way. And if you assume charge conjugation going to this way, then you can confirm that this is of course charge conjugation invariant by construction. This is also invariant. But this one vanishes because that's a left-handed projection, but this goes to the right-handed. Therefore, again, rather ill-defined those things going on. Therefore, the Majorana-Weil equivalence is, in a sense, very subtle when it comes to the quantum field theory. And the same thing happens, for example, if you want a weak interaction, standard model, then this is a left-handed weak interaction. And everybody knows that this is C and P violating. But this also can be written in this form. And if you use this first expression and seesaw-like charge conjugation, then you recognize this is a C invariant. And if you use this one, then this goes to 0. Therefore, again, very ill-defined operation. And because of this ill-defined operation, and in the seesaw Lagrangian, original Lagrangian is C violating, but after rewriting it by the Majorana, then perfectly C invariant like that happen. But our proposal is that to use the relativistic analog of Bogoliubov transformation. And we just discussed this one. And transformation looks like this, rather complicated, but anyway, particular and anti-particles are mixed, and the gamma fiber appears, and the angle is this. And we apply this in the this seesaw Lagrangian. Okay. Then that transformation satisfies the canonical property. That's basically required to Bogoliubov, but you can confirm it. Namely, using the right-hand side, you can confirm that all the anti-commutators are the left-hand side. And also that the seesaw Lagrangian becomes like this after this transformation. And the interest point that the epsilon 5, which broke charge conjugation, behaves like the energy gap in BCS and absorbed into the mass term of the Dirac type 1. And this is the C conserving part. So nothing wrong. And therefore, this becomes massive by absorbing this part. So we call this the analog of the Bogoliubov transformation because in the BCS theory, after Bogoliubov, the charge charge non-conserving part of BCS is that some absorbed is a mass term. Therefore, under Lagrangian for the quasi-particle NX, we call it quasi-particle because that's the after Bogoliubov transformation, people often call it quasi-particle. And that Lagrangian, if you redefine this way, then you can diagonalize this way. That's the exact way, mass is this one. And this smaller mass agrees with the usual formula of seesaw mechanism. For example, typical value is this, then you get this mass value. And when this is very small, you can expand it. Then leading term is this seesaw formula. So give the small neutrino mass. And also charge conjugation of the Majorana is follows the charge conjugation of the N, which is well defined in the Lagrangian. And then for further check, left-handed component of neutrino, which describes the weak interaction, is written in this form, in our formulation. And this is a very small ratio in the seesaw mechanism. So nu L is almost the all left-handed smaller mass neutron, say Majorana, left-handed one. And the charge conjugate of this one is, in our case, have this one. And you see that the charge conjugation Majorana, charge conjugation of the starting while are very different. Because C sends Majorana go to this way, C nu sends the neutrino go to C nu L. But therefore this goes to this goes to this. But this is almost zero, this is unity. This is almost unity, this is zero, this goes to this. Therefore, this is the explanation why in the seesaw mechanism, very badly broken by the very gigantic right-hand mass that breaks parity and C. But still, you can define the nice Majorana. From this point of view, my view is rather natural. And Majorana neutrino that defined in terms of this, I call the Bogoliubov quasi-particle, we suggest the idea of Majorana neutrino maybe a Bogoliubov quasi-particle. And then it will be interesting to see how the vacuum of Bogoliubov quasi-particle differs from the naive vacuum of Dirac neutrino, for example. And we discussed this problem following the analysis of Nambu and Jonarasinio. So in this sense, relate to Nambu. And the conventional Bogoliubov transformation as formulated of Nambu Jonarasinio go this way. After spontaneous generation of nucleon mass, they have this. And then this is a massless nucleon before spontaneous breakdown. And then Bogoliubov transformation, they define this. Although they don't call it Bogoliubov, but I believe this is Bogoliubov. And they set this equality. Namely, at the very specific time t equals 0, exact solution of this one is equate to exact solution of this one for all x. And first of all, this is a canonical, because using this, you can evaluate the canonical anticommutators, something like this. Therefore, this satisfies the Bogoliubov transformation. Also, if you solve the creation and annihilation operators in terms of creation and annihilation operators, then that operator diagonalizes this Lagrangian. So that is essentially the Bogoliubov transformation does. So creation and annihilation operators expressed one satisfy the usual commutators. And when you solve that equation, then these are the massive particle and anti-particle annihilation operators in terms of massless annihilation and creation operator. So in this scheme, it is typical that the A, B 段が creation annihilation operator mixing takes place. And I believe that this is an artifact of the breaking of relativity and so on. But anyway, in the purely relativistic case, in our relativistic analog, we don't have this kind of mixing. But anyway, you have that operator. Therefore, you can impose quasi-nucleon vacuum. Should be 0. And then you can solve it in this form. This is a starting massless nucleon vacuum. And then you will see that the particle and anti-particle, say, nucleon, anti-nucleon massless pair condensation with chirality plus minus 2. So you get a very nice idea what's going on in this picture. That's what Nambu generation does. So we just imitate it. So here one example, the Dirac neutrino corresponds to the massless nucleon case of the Nambu generation. And we add this one. This is the C symmetry breaking. And after Bogoliubov, this becomes very massive. This one is converted into the mass term. Okay? Therefore, we treat this as an analog of the mass term of the Nambu generation. By the way, this one is a charge conjugation-wise invariant. But this charge conjugation is broken by this. Okay? Therefore, if you replace charge conjugation by chiral transformation, then very much like the Nambu generation. So epsilon 5 is an analog of the chiral symmetry breaking mass term of Nambu generation. And then we impose Bogoliubov condition a la Nambu generation. Namely, this is this one is an exact solution of the Dirac type neutrino. This is an exact solution of that C violating extra term, also fermion number violating. But in term after Bogoliubov transformation, you can write it in the exact solution. This is the exact eigen state. And then you can solve this one in terms of creation annihilation operators, and you can impose this kind of condition, namely ground state of the quasi-particle. In our case, N field, and in the case of the Nambu generation, that's a massive nucleon. And then if you impose this one, because the annihilation operator, then for the very small limit of the epsilon 5, namely very small C violating, that is very close to the Dirac point. Therefore, rather unphysical from the point of view Seesaw. But anyway, just to see what happens, we analyze it. Then what happens that now vacuum, which is fermion lepton number plus minus 2, because this is a lepton creation operator, it's an anti-lepton creation operator. And also, if you apply the original charge conjugation, that is the charge conjugation of the Dirac neutrino, then you can find that this vacuum is not invariant. This shows that this condensation carries a charge conjugation symmetry. Therefore, this is not only violate lepton number, but also violating the charge conjugation. And this is consistent with our expectation, because I have explained that the charge conjugation of the Seesaw, the Majorana in the Seesaw, and the charge conjugation of the starting Lagrangian of the Seesaw are very different. And in fact, in this case, very different. And therefore, vacuum is regarded as a vacuum of condensed C symmetry, when C from the original vacuum and different. So this is a good illustration of vacuum of the quasi-particle. But not spontaneously breaking, because Bogoliubov transformation is very much kinematical transformation. Therefore, for example, in our example, we did not discuss no dynamics of the, for example, condensation creation, that's to say, epsilon creation. And therefore, in the Nambu general scenario case, essential idea is how to generate a nucleon mass. But if you want to generate nucleon mass, then Bogoliubov transformation gives a nice way to diagonalize the energy or mass, and you can recognize so-called quasi-particle. And so in that sense, our N particle might be called Bogoliubov quasi-particle. So conclusion is that the maybe ending too early, but anyway, our relativistic analog of Bogoliubov transformation and the conventional Bogoliubov transformation, which is intrinsically non-relativistic, are rather different. For example, our Bogoliubov has no mixing of positive and negative frequency components, but still absorbs mass gap, C by radiative condensation. So in that sense, maybe called quasi-particle. So our suggestion is that the Majorana neutrino, if observed, may be identified as the first Bogoliubov quasi-particle among elementary particles in this sense. And if you don't like this idea, but still I believe that our Bogoliubov transformation is a nice way to understanding the why charge conjugation violating Lagrangian of the seesaw mechanism. Namely, seesaw mechanism that you add a very heavy right-handed mass term, so which inevitably breaks parity. Say if you impose Cp, then C is broken. But nevertheless, this is a quadratic form, therefore you can rewrite this exactly in terms of the Majorana. Then somehow perfectly C invariant, and that is somewhat mysterious, but I believe that our way of understanding like this, namely original physical neutrino is comes from this one, and some mixing. This means charge conjugation is violated, but anyway, manifest shows it. But at the same time, this charge conjugation breaks are enormous, because C is broken by the very, very heavy, say 10 to the 15th GeV right-handed mass, for example, neutrino. So enormous breaking is shown in this formula that you say. So that's all.
Thank you so much.
Yeah.
Professor Fujikawa, we have very little time for one or two questions. Anyone want to raise any question? It's a very interesting talk. No question? So we thank Professor Fujikawa again.